You know that moment, don't you? You're interacting with a really sophisticated AI system, one that can craft an amazing poem or generate these stunning images, summarize complex stuff in seconds, and then you ask it something that feels, well, simple, like, I don't know, if my car breaks down on the way to the moon, what's the cheapest tow? Or maybe, can a square circle exist?
Right, something that requires a bit of common sense or just factual grounding.
Exactly. And it confidently, fluently gives you an answer that is just completely nonsensically wrong. It sounds plausible, grammatically perfect often, but factually way off.
Yeah, that phenomenon, we often call it hallucination. It's a huge frustration.
It really is. And it's kind of the Achilles heel for even the most powerful AI systems we have today, isn't it?
Absolutely. It highlights this fundamental tension, this sort of gap in AI development.
We've seen these incredible breakthroughs, right? AI recognizing faces instantly, translating languages on the fly.
Generating art that's, well, it's hard to tell from human work sometimes.
But then, like you said, it just stumbles on basic common sense.
Or it struggles with verifiable facts, logical consistency. It's like having this brilliant savant, someone who can compose a symphony but then asks if the sun rises in the west.
That's a great analogy. The gap between the statistical prowess and fundamental understanding, it can be jarring.
Definitely jarring.
So, okay, that brings us right to the core of our deep dive today. How do we engineer machines that have both that imaginative, pattern-recognizing brilliance we see and the rigorous, reliable reasoning ability, the part that ensures truth, common sense, and crucially, trustworthiness?
How do we build an AI that's not just statistically clever, but genuinely smart, reliable smart, especially when the stakes are high?
Exactly. How do we get both?
Well, today we're going to unpack Neuro-Symbolic AI. And look, this isn't just some incremental update. It's not a minor tweak.
Okay.
It really represents a groundbreaking shift. It's a deliberate attempt to forge this powerful alliance between two historically separate ways of thinking about AI.
Two philosophies, really?
Exactly. It proposes a true marriage, a deep reconciliation between the pattern-hungry neurons of deep learning and the precise rule-based logic of classical AI.
Okay, neurons meet logic.
That's the core idea. And our mission here is to reveal how this synthesis, this combination, promises to build AI that isn't just smarter, but profoundly more trustworthy, more understandable, and frankly, far more capable of genuine human-like reasoning.
All right, let's unpack this. Neuro-symbolic AI. It sounds fascinating. So to really get what it's trying to do, we need to understand those two pillars first, right?
Yeah.
The ones it's trying to bring together.
That's right. We need to lay the foundation. So on one side, you've got the connectionist approach. This is mostly what we hear about today. Neural networks, deep learning. Think of these as, well, intuition on steroids.
Intuition on steroids. I like that.
Yeah. They're inspired by the brain, right? Millions or now billions of these interconnected nodes, these neurons, processing info in parallel. And the key is they learn complex patterns directly from massive amounts of raw data, images, audio, text.
Just by looking at examples.
Exactly. By constantly adjusting the numerical strengths, the weights of their internal connections. It's like building intuition purely from experience, seeing so many examples that patterns just emerge.
And their strengths are, they're genuinely revolutionary. That's undeniable. They're amazing at learning from raw, messy data. They don't need humans to handcraft rules for them to find relevant patterns.
No, they discover features on their own. That's the power. It's the bedrock of modern machine perception, facial recognition, understanding language.
And they're adaptable. They generalize.
They do. They adjust their internal settings, their parameters through training so they can make predictions on new data they haven't seen before.
Yeah.
As long as it's statistically similar, of course.
Right. Similar to the training data.
And they handle noise pretty well, too.
Yeah.
Messy, real-world inputs.
Like understanding your voice in a noisy room.
Exactly. Or finding an object in a blurry photo. And they're fast. Because they're so parallel, they just fly on modern hardware like GPUs. They are incredible pattern matchers.
Okay, sounds amazing. But then you hit the wall.
Then you hit the wall.
The famous black box problem.
Right. Their decisions are opaque. They're spread across millions, billions of these numbers.
So if an AI recommends a stock or maybe suggests a medical diagnosis,
you have almost no idea why. What was the reasoning? It's just the numbers came out that way.
And that lack of transparency, that's a huge barrier to trust, isn't it? Especially in fields like medicine, finance, self-driving cars.
Absolutely. Anywhere, accountability is key. You need to know the why.
And beyond the opacity.
Well, they are incredibly data hungry, astronomical amounts of data, often labeled data, which is expensive and time-consuming to create.
So data scarcity is a big problem.
It's a huge bottleneck for many problems. And then there's a really critical limitation. They're actually quite poor at causal and abstract reasoning.
Okay, explain that. They see patterns, but...
They see correlations, very sophisticated correlations, but they don't truly understand cause and effect. They learn that smoke often appears with fire because they see it countless times in the data.
But not that fire causes smoke.
Precisely. They lack that fundamental model of how the world works, which leads to this profound lack of common sense.
Like the object permanence example.
Yeah, exactly. A neural net might need millions of examples to learn that an object still exists when hidden. A baby gets that intuitively, very quickly. It's a different kind of learning.
And they can be brittle too, right? Despite handling noise.
Surprisingly brittle, yes. Tiny changes to the input, sometimes imperceptible to us, these adversarial attacks, can make them fail catastrophically.
Like misidentifying a stop sign because of a few changed pixels.
Exactly that kind of thing. It's like a marathon runner tripping over an invisible pebble. Seems robust, but has these odd vulnerabilities.
Okay, so that's the connectionist side. Intuition on steroids, but black box, data hungry, lacks common sense. What's the other pillar? The classical approach.
Right, the classical approach, often called symbolic AI or sometimes GUF-AI, good old-fashioned AI. This was the dominant way of thinking from the 50s through the mid-90s. Think expert systems.
Okay, so how does that work?
It's about manipulating explicit symbols. Things like dog, mammal, ISA, HASFER, according to predefined logical rules and knowledge structures.
Ah, so it's like programming logic directly, like legal codes for machines.
That's a great way to put it. Its core strength is logical reasoning. Precise, step-by-step deduction, induction, applying rules with mathematical rigor.
If A implies B and A is true.
Then B must be true. Foundational logic built right in.
And they're good at representing knowledge.
Excellent at it. Using human-readable frameworks, first-order logic, if-then rules, ontologies that define concepts and relationships.
Which means transparency.
Total transparency. The decision-making process is completely open. You can inspect the facts, the rules it used, the whole chain of inference.
So you know exactly how it reached a conclusion.
Exactly. Highly debuggable, formally verifiable. You can often mathematically prove they're correct for their domain. That explainability is a massive advantage.
So they worked well in specific areas, like early medical diagnosis systems.
Precisely. In well-defined, constrained domains where rules govern behavior, they excelled. Precision and domain knowledge were key.
They obviously had weaknesses too, or we wouldn't need neural networks.
Oh, definitely. Big weaknesses. They're notoriously brittle when facing the real world's messiness.
Okay, brittle how?
They operate perfectly within their programmed rules. But give them noisy, ambiguous, or incomplete data, anything slightly outside their perfect world, and they often just break, fail completely.
Because the real world isn't neat logical rules.
Not even close. It's messy, ambiguous, uncertain. Symbolic systems really struggle with that.
And getting the knowledge in there in the first place.
The knowledge acquisition bottleneck. A classic, massive problem. Manually encoding comprehensive knowledge for complex domains. Incredibly hard, slow, expensive.
You need human experts to painstakingly translate everything into formal rules.
Right. It just doesn't scale to the kind of broad, nuanced understanding needed for general intelligence.
And they don't learn from data like neural nets do.
Traditionally, no. They're static. Knowledge has to be updated by programmers. And they also struggled with probability reasoning under uncertainty, which is vital for the real world.
Okay, so two very different approaches. Connectionist learns from data, perceptive but opaque, and lacks common sense. Symbolic, logical, explainable but brittle, and struggles with messy data and learning.
Exactly. And here's the really compelling part.
What's that?
The weaknesses of one are almost perfectly the strengths of the other.
Ah, they complement each other.
Beautifully. It creates this powerful, almost irresistible argument for integrating them, bringing them together.
It makes intuitive sense.
And the best way to think about this integration, this neurosymbolic idea, is through psychology. Daniel Kahneman's model of human thinking.
System 1 and System 2, I've heard of this.
Exactly. System 1. Fast, automatic, intuitive, unconscious. Recognizing faces, understanding tone, reacting quickly.
Based on patterns, experience, low effort.
That's our neural network counterpart, the perfect System 1 for machines. Rapid, parallel, intuitive pattern matching.
And System 2.
Slow, deliberate, analytical, conscious. Logical reasoning, complex calculations, planning a strategy. Requires effort.
That sounds like the symbolic side.
Precisely. Explicit rules, logical inference, sequential reasoning. The ideal system, too, for machines.
Oh, okay. Let's use the driving example you mentioned. That makes it concrete.
Right. You're driving. Your system 1, your neural intuition, instantly spots a red light. Automatic pattern recognition, no conscious thought needed.
You just see red light, danger.
But then your system 2, your symbolic reasoner, kicks in consciously. It processes traffic laws. Red means stop. Interprets signs, no turn on red. Calculates speed, braking distance, position of other cars.
All the logical steps.
Right. Combining all that explicit knowledge and reasoning to make the deliberate decision, apply the brakes, stop safely. It's a seamless blend of perception and reasoning for us.
So the core idea, the thesis of Neuro-Symbolic AI, is to build machines that mirror that.
Exactly. To build AI with that same powerful cognitive architecture, leveraging a neural system 1 for perception, learning from data, generalization, and pairing it with a symbolic system 2 for deliberation, rigorous reasoning, logical consistency, and justification.
So it's not just about perceiving the world, but truly understanding it, thinking about it using structured knowledge.
And critically, justifying its decisions. It's about AI that can see, think, and explain itself.
Okay, that's a compelling vision, but why now? Deep learning has been on such a roll. Why the push for this integration now?
Well, precisely because despite that incredible third AI summer, the limitations of pure deep learning are becoming much clearer, even painfully so.
We're hitting some walls again.
We are. Pure neural models fundamentally are these super sophisticated correlation engines. They find statistical links, but they lack
Genuine understanding, common sense.
exactly that. They don't have an underlying model of why things happen, just that they often happen together in the data. They lack causality. Which leads back to that common sense gap. They struggle with basic intuitive concepts humans grasp easily, like gravity, object permanence. They might predict what happens, but not understand why.
And that leads to the hallucinations we started with.
Directly. Because they're generating based on statistical likelihood, not grounded facts or logic.
And the black box problem hasn't gone away either.
Not at all. Still a huge hurdle for trust. That opacity makes them unsuitable for critical, regulated areas, medicine, finance, autonomous systems.
Where you absolutely need to know the reasoning. Accountability is non-negotiable.
Non-negotiable. And the reliability crisis with large language models, the hallucinations, that erodes trust and limits where we can safely deploy them. Factual accuracy is paramount in many applications.
Plus, the resource cost, the data and compute hunger.
It's immense. Training these state-of-the-art models needs astronomical data and compute. It's expensive, environmentally taxing, and limits access. It raises questions about sustainability and democratization of AI.
It feels like just throwing more data and compute isn't necessarily the smartest long-term strategy.
Many are arguing exactly that, and this is where neuro-symbolic AI comes in as a potential antidote.
How so? How does it address these specific problems?
Well, first, by explicitly integrating symbolic knowledge graphs, rule sets, ontologies that encode common sense facts, causal links, it moves beyond just pattern matching. It gives the AI a foundational model of how the world works, an internal reality check.
So it can infer, extrapolate, understand situations better, not just correlate.
Exactly. In a way, pure statistical systems just can't. It provides a grounding.
And what about trust, hallucinations, explainability?
By coupling the generative neural models with verifiable symbolic knowledge bases, the symbolic part acts as a logical guardrail.
Logical guardrail.
Yeah.
Or logic seatbelts, as you said earlier.
Yeah, logic seatbelts. I like that one. It fact-checks outputs in real time, ensures consistency with known facts and constraints.
And because the symbolic reasoning is traceable.
The whole system becomes explainable. It can justify its outputs by pointing to the specific rules and facts it used. It shows its work.
That's huge. It prevents veering into factual errors and explains why.
It builds trust, fundamentally.
But what about the efficiency? Doesn't adding symbolic stuff slow it down or require that old knowledge bottleneck again?
Actually, it's the opposite regarding efficiency. By incorporating prior knowledge through the symbolic part, the system doesn't need to learn everything from scratch via data.
The knowledge acts like a scaffold.
A perfect analogy, a learning scaffold. It helps the neural network generalize effectively from far less training data.
How much less?
Research shows neurosymbolic systems can sometimes reach top performance with as little as 1% to 10% of the data purely neural systems need.
1 to 10%. That's a massive difference.
It's drastic. It makes AI development potentially much more accessible, sustainable, less reliant on massive data sets and compute. It challenges that bigger is always better scaling paradigm.
Okay, this isn't just theory anymore, right? You mentioned breakthroughs happening now.
Absolutely. We're seeing tangible results. One really stunning example is in mathematics, Olympiad-level geometry problems.
And like the really hard stuff from international math competitions.
Exactly. There's a system inspired by these neuro-symbolic ideas that's performing at the level of human gold medalists, solving around 88% of these incredibly tough problems and doing it fast.
Wow. How? Is it just brute force proving?
No, that's the beauty of it. It uses a neural language model, it's System 1, to intuitively suggest useful steps, like a human mathematician sketching auxiliary lines having an insight.
So the neural net provides the creative spark.
Kind of, yeah. It proposes promising geometric constructions. Then it hands these over to a System 2, a symbolic deduction engine.
The logic.
Right, which rigorously explores these suggestions, applies axioms and theorems, and formally proves them step by step with mathematical precision.
It's the intuition combined with rigorous proof.
That elegant collaboration.
So what? What does this mean practically?
It means AI is becoming a true partner in complex problem solving, not just a data cruncher or answer machine. It can show its work, help us discover new approaches. It opens doors for smarter tools in engineering, science, math, anywhere you need intuition and proof.
That is really cool. What else?
Well, think about high-stakes areas like defense or disaster response. There are initiatives like DARPA's NSR program developing hybrid drones using these principles.
Drones that can explain themselves.
Exactly. Battlefield-grade drones that don't just identify a potential target, but can explain why they classified it as such, providing that crucial accountability.
So what's the impact there?
Safer, more accountable autonomous systems. Not just military, but think disaster response robots, search and rescue, even future self-driving cars needing to justify emergency maneuvers. Trust is paramount.
Makes sense. And for common sense, that big hurdle for neural nets.
Researchers are building modular logic blocks. Think of them as plugins called composable attentive reasoning networks.
Logic plugins for language models.
Essentially, yes. They plug into large language models, the transformers, and allow direct integration of common sense inference rules.
So the AI can reason more deeply about everyday situations.
Precisely. Understand context better, provide logically consistent answers, make fewer of those silly common sense mistakes.
So what does that mean for me talking to my voice assistant?
It means conversational AI that genuinely gets it. More effective, less frustrating chatbots and assistants, because they're not just predicting words, they're reasoning sensibly.
Okay, and the hallucination problem, the logic seatbelts.
Industry labs are actively integrating these neuro-symbolic guardrails into their big language models right now.
Really? So they're using symbolic knowledge bases to fact check?
Yes. Coupling the generative power with verifiable facts and rules. The symbolic part acts as that real-time fact-checker, ensuring the output sticks to known constraints, drastically reducing hallucination rates.
So what? Why is that a game changer?
It makes generative AI reliable enough for critical tasks.
Right.
Legal drafting, medical support, financial advice, areas where factual accuracy and accountability are absolutely critical. It turns a potentially unreliable tool into a trustworthy one.
Wow. Any other areas?
One more really interesting one. Brain research is showing our neurons actually forecast multiple possible futures at once, not just predicting one outcome, but simulating options.
Our brains do that.
Seems so. And this is inspiring next-gen neurosymbolic systems capable of predictive symbolic planning.
So AI that can anticipate outcomes better?
Yes. They learn from data, but also build richer models of the world to anticipate consequences and plan sequences of actions more effectively, like human intuition combined with strategic thinking.
So what could that lead to?
AI that excels at complex strategic planning, optimizing traffic flow, global logistics, or personal assistants that anticipate your needs with uncanny accuracy. Truly proactive intelligence.
Okay, let's bring this down to earth. Where will people really feel the impact of neuro-symbolic AI? Where does it make a tangible difference?
Great question. Healthcare is a prime example. Imagine getting a second opinion on a radiology scan.
Okay.
A neurosymbolic tool uses its neural net, its System 1, to spot subtle patterns in the X-ray, maybe suggesting early pneumonia.
The perception part.
Right. But then its symbolic reasoner System 2 steps in. It checks clinical guidelines, patient symptoms from the record, And it explains, I suspect pneumonia because I see pattern X neural perception, and this, combined with reported fever and cough, aligns with Rule Y from the clinical guidelines symbolic reasoning.
So it's not just, I see something, but I see this, and here's the established medical logic connecting it to your symptoms.
Exactly. It transforms a black box suggestion into a transparent, verifiable medical insight. That builds huge trust for doctors and patients.
That's incredibly powerful. What about autonomous systems? Cars, drones?
Accountability is key there. A self-driving car uses neural nets to perceive objects, cars, people, lights, instant perception.
System 1, seeing the world.
Then its symbolic planner system 2 takes over. It reasons about traffic laws, safety rules, its goal, plotting a safe, legal path.
And if something happens, an accident, or even a near miss?
Crucially, it can explain its actions. I detected an obstacle neural perception, and based on traffic rules and safety protocols symbolic reasoning, I initiated an evasive maneuver.
That clear, auditable justification is vital for trust, regulation, liability.
Absolutely essential for widespread adoption.
And for developers, you mentioned bug-free code. That sounds almost too good to be true.
It's a potential revolution for software engineering, honestly. Neuro-symbolic systems could combine the knack of neural models for generating plausible code from descriptions.
Like you tell it what you want, it writes the code draft.
Right, but then it pairs that with symbolic formal methods, basically, mathematical techniques, to prove that the generated code is correct, secure, bug-free.
So it doesn't just write code that looks right, it writes code that's mathematically verified.
For critical parts, yes. The symbolic component acts as a built-in verifier. Imagine getting guaranteed bug-free code for certain functions. That could massively speed up development and improve reliability, especially for critical software.
Okay, let's try that mini store you mentioned, the robot furniture assembler. That sounds like a good test.
Right, so scene 1, neural perception. Picture this robotic arm. It's hovering over a messy pile of flat-pack furniture parts. Camera sees it all. Its neural vision system, the system 1, instantly processes this chaos.
Yeah.
It doesn't need labels. It just recognizes based on training.
That's the tabletop. Those are legs. Bag of screws. Even knows how they're oriented.
Exactly. Precise position and orientation. It just sees and understands the visual world like we do. It gets the what.
Okay, it sees the pieces. Now what? How does it know how to assemble it? That's where common sense comes in.
Precisely. Scene 2. Symbolic reasoning. Now the symbolic system, the system 2, takes over. It accesses a structured knowledge base, like a digital instruction manual, combined with physics rules.
Rules like part A connects to part B, tighten screws before next step.
Exactly. In physical constraints, you can't put a screw where there isn't a hole. It logically sequences the actions based on these rules. First, attach leg braces to tabletop. Then, fasten legs with screw type X. Ensure torque Y is met. Step-by-step logic.
So it avoids errors a purely perceptual system might make, like trying to attach things in the wrong order or upside down.
Right. It ensures each step is correct and physically possible. It knows what the pieces are from System 1 and how to assemble them correctly using System 2.
It's that seamless blend of perception and logical planning, seeing and understanding, then reasoning and acting.
That's the essence of it. Robust, reliable, intelligent action.
Okay, it all sounds incredibly promising. But it can't be easy. What are the big technical hurdles? Where's the difficulty in making this work seamlessly?
Oh, there are definitely significant challenges. It's not just plug and play. Merging these two fundamentally different ways of computing is hard.
Like teaching two different languages to speak to each other perfectly.
Something like that. One major issue is the scalability conundrum.
Meaning, can these hybrid systems ever be as fast or handle as much data as pure deep learning models?
That's the question. Deep learning models are super optimized for GPUs, massive parallel processing. Symbolic reasoning, especially complex logical inference, can be computationally expensive. Searching through logical possibilities can explode.
So the symbolic part could become a bottleneck, slow things down.
It could, yeah. Which leads to this kind of philosophical debate. Do we just keep scaling up the current deep learning models, bigger, more data, more power?
The brute force approach.
Right. Or do we pursue this different kind of intelligence, one that's maybe more efficient, more robust, more understandable, even if it's not purely about raw speed?
Doing more with less, using knowledge, like the human brain on 20 watts.
Exactly. Designing smarter systems, not just bigger ones. It's a different philosophy.
Okay, scalability is one thing. What about actually training them together?
That's the training tightrope. It's really tough. Neural networks learn via continuous adjustments, like turning a smooth dial gradient descent.
Small steps downhill to find the best setting.
But symbolic logic is discrete. Rules are true or false. There's no smooth in-between to adjust slightly. You can't easily backpropagate errors through a logical query like you do in neural nets.
So how do you get them to learn together?
Researchers are trying different things. Loosely coupling them, train the neural net, feed output to the symbolic part. Using reinforcement learning, symbolic success reinforces the neural net. Or developing these complex, differentiable surrogates, trying to make logic operations look smooth enough for neural nets to train with. Very cutting-edge stuff, like logic tensor networks.
Sounds complex. And what about getting the knowledge in? Does the old knowledge acquisition bottleneck come back?
It doesn't disappear, it evolves into a knowledge synchronization problem.
Synchronization.
Yeah, it's not just how do we build a knowledge base, it's how do we keep that knowledge base consistent and up to date as the neural network learns new things from messy real-world data.
So if the neural net learns a new concept,
does the symbolic knowledge base need a manual update? Or can the system learn to update its own truth source? Which sounds great, but is risky if it learns wrong things.
maintaining that dynamic consistency between the learned stuff and the structured knowledge, that sounds really hard.
It's a profound, unsolved challenge. Ensuring the integrity of that interaction is key.
You had a metaphor for this.
Yeah, it's like trying to get a free-flowing improvisational jazz band and a precise score-reading string quartet to perfectly sight-read the same complex piece together, instantly.
Bridging the continuous intuitive world with the discrete logical world, making them speak the same language harmoniously.
Exactly. That's the core technical challenge.
Okay, so challenges exist. But despite them, you're optimistic about the near term. What can we realistically expect soon, say in the next year or two?
Very optimistic. We're talking tangible improvements soon.
Like what?
Voice assistants. Within 12 months, expect significant steps. They won't just fetch info. They'll start cross-checking your calendar, preferences, external data using logical rules.
So they'll be factually grounded, contextually aware.
Much more so. Imagine an assistant that doesn't just find an empty slot, but avoids scheduling something because it reasons about your travel time, existing commitments, maybe even your stated preferences.
Moving from info retrieval to actual intelligent planning.
That's the leap. Genuine utility, not just convenience.
What about professional tools? Legal tech?
We'll see legal engines drafting complex clauses, using neuro-symbolic principles not just to generate legal-sounding text, but ensuring the clauses are logically sound, consistent, and traceable back to specific precedents or regulations.
Built-in verification and accountability for legal drafting.
Unprecedented accuracy and accountability, saving time and reducing errors.
And education. STEM tutors.
Get ready for STEM tutors that really teach. They won't just give answers. They'll meticulously prove each step of a math solution or explain a scientific concept logically.
Showing the why behind each step.
Exactly, walking you through the inference chain, fostering deep understanding and critical thinking, not just memorization, like a patient, logical tutor available 24/7.
So wrapping this up, what we've really explored today is this necessary evolution in AI, right? This deep integration of learning and reasoning.
It really is. Combining the intuitive perception of neural nets, the digital system 1, with the rigorous, explainable logic of symbolic systems, the digital system 2, it feels less like an option and more like a critical path forward.
Moving towards, as you put it, intelligence by design, not just hoping intelligence emerges from scale alone.
Precisely. Being deliberate about building in understanding, reasoning, justification capabilities we know are key, rather than just scaling up and hoping for the best.
And fundamentally, this third wave isn't just about more power. It's about trust.
It's fundamentally about building machines we can trust. Neuro-Symbolic AI offers inherent transparency, explainability, verifiability. That means tools that can reason with us.
Showing their work, explaining decisions.
Aligning with human intent and values in a way we can actually see and understand.
It sounds like a more deliberate, maybe safer path towards more general beneficial AI.
I think it represents that, yes.
Yeah.
A roadmap emphasizing accountability and understanding.
So as you go about your day, maybe interacting with current AI, think about this potential. What fascinating new problems, what amazing possibilities could you imagine tackling with an AI that doesn't just learn, but genuinely reasons right alongside you?